get on with the McCulloch's and Pitts model. So MCP is the McCulloch's and Pitts model, which is typically also called an MCP model. You have essentially, basically, so it is a node. In a neuron basically is a processing unit of a neural network. It is a node that processes and fans out to all other nodes, as I explained previously, and it generates an output according to a transfer function, which we call an activation function. You're used to these things like ReLU. You've heard of ReLU. You've heard of activation functions like sigmoidal, obviously, and then you've heard of the activation functions like DANH and a bunch of other. Google also came up with a brute force model we call Swish. Models or activation functions like these. So if we just kind of mathematically kind of sketch out how a McCulloch's and Pitts model, you've seen that, right? So you have an input, so and just sketch it out, and then we can go into the details of what it looks like. X2, and then we can kind of do XG1, and essentially there you have. And so color this a little bit, and then you have your summation. This is your activation function, essentially. That's your activation function. And then you have your output. Cool. So basically what you're seeing here, the output of the neuron is given by this. That's your output. And just create a new slide. So basically what you just saw here is essentially, this is your network. And just sketch these out first. This one, G1 is total number of outputs. W of I, X of I, minus theta, which is your bias. Weight transposed, X minus theta. And then you have your Y. So essentially this is your first equation. And then you pass in your activation function, you pass the network into your activation function, and then that becomes your output, essentially. So basically here, let's go back to the other. So Xi essentially is your EAT input. So Xi is your EAT input. Wi is your rate, or you can also call it a link rate of your EAT input, where your W is W1 all the way to WJ1 transposed. And then you have your X is your X1 XG transposed. And theta is your threshold value. So theta is your threshold, or actually this is your bias, right? As I mentioned before. And J1 is your number of inputs. So essentially, and what you also see, the activation function, how much space here. So maybe just kind of go into the activation function, which is your phi is usually it's a continuous or discontinuous function. I'll just say discontinuous function that essentially mapping the real numbers, right, between -1 and 1, or 0 and 1. So let's go back. So here you have your MCP model. These are your inputs. You pass in your activation function. You have your output. They look like these. And essentially, so, this is how the McCulloch's and Pitts neuron model was constructed. So VLSI is basically very large-scale integration. It's a process of creating integrated circuit IC by combining millions of transistors onto a single chip. That's what it is. Now let's take a quick look at it and see if you can kind of draw this quickly. So VLSI, and we have a similar model like we just drew for the McCulloch and Pitts, X1, X2, and then we have XJ1. And draw these basically, and this guy, so this guy heads for the positive potential, and we have the negative potential towards the bias, which is a theta. And everything. And then here you have your output. Obviously, you apply your, this guy, phi, the activation or transfer function. This is your W1, W2, WJ1. So basically, this is how a VLSI model for a neuron looks like. And very quickly going through the VLSI circuit implementation, the analog approach is super attractive in terms of actually three things, which is size, speed, and power. And this is where the VLSI becomes super interesting and for neuromorphic chips that are being developed. Neuron can be realized with a simpler amplifier. So basically, this is your neuron. The simple amplifier, you can just look at it as an amplifier. And your synapse is a resistor. So basically, essentially, your synapse is your resistor. And let's create another sheet. Here, basically, according to the Kirchhoff's current law, we just apply the Kirchhoff's current law, the output voltage, which is your Y, so your output voltage is equal to your activation function. And here you have your J1, I is 1, W of I, X of I divided by summation, I is 1, J1, W of I minus theta, which is your bias. So that's the output voltage of your neuron. Here you have, what is X1? Xi is your ith input voltage. W of I is your conductance of the ith resistor. Theta is your bias, and phi is your transfer function, or that's your activation function, right? You're familiar with that. So basically, the bias voltage of a neuron in a VLSI circuit is caused by device mismatches. This is caused by device mismatches and is not always easy to control. And we've seen the McCulloch's and Pitts neuron model is actually known as a classical perceptron model. So MCP is a classical perceptron model. We've drawn these also in my classes that you guys have been part of. And it is used in most neural networks, including the MLP multi-layer perceptron, which we've drawn, and the Hopfield network. So I'll just stop here, and then we'll try to recap this all together.